Welcome to lecture number 2 for ECE 341 Random Processes. In this lecture, we're going to go over Monte Carlo simulations. So this is one of the lectures one of the courses that's on Bison Academy. Bison Academy is the semi-official website for the Electrical Computer Engineering Department at NDSU. In it, it's got courses, quite a few courses in electrical, and part of the intent is we want you to use knowledge from prior courses. If you've had Circuits 1, Circuits 2, whatever, and you need a refresher, all the lecture notes, homework set solutions, recorded lectures, and so on are posted free to use on Bison Academy. This course is 341 Random Processes, and we're right here on lecture number 2, Monte Carlo. Plus, you can also see the future lectures if you want to look ahead. If you want to go back and refresh your memory, previous lectures are available in PDF format as a recorded YouTube video, along with sample code and homework sets and solutions. So carrying on. Now this course, Random Processes, is all about, basically it's a course on statistics. Where we want to get to is at the end of the semester doing analysis of data. When you go into the lab and collect data, every time I run the experiment I'm going to get different answers. Statistics is the mathematics of random processes, events where the outcome is different every time. Now, in terms of probability is really defined as the number of times or percent of times an event happens as the number of trials goes to infinity. That's really what we mean by the probability. If the probability of A happening is 0.1, if I roll the die 1,000,000 times, or going to infinity, 10% of the time I'll get the result. That's what probability means. Now that kind of leads to one way to calculate probabilities that works really well with Matlab, called Monte Carlo. A Monte Carlo experiment, well, the idea behind Monte Carlo is if I can write a program to play a game one time, that I can put that in a for loop and play the game 1,000,000 times and simply count. How many times does the event happen in 1,000,000 rolls? Roughly, that'll be the probability of the event. That's called a Monte Carlo experiment. And Matlab is a really useful tool in doing that. Basically, Matlab is a calculator. So to illustrate what Matlab looks like, Matlab's a program that it's free to all NDSU students. NDSU pays for site license, so all students can use it. You need to install it. You can actually use Matlab online. There's an online version that's a lot slower, more convenient if you download it on your laptop. And definitely recommend downloading Matlab onto the computer you're going to be doing the homeworks on in this class. So this is what Matlab looks like when you start it up. It's got a bunch of different windows. This is a list of all the different files in my current directory. I don't care. Close that down. Here's a list of all my variables. I don't care. Close that down. List of all my previous commands. I don't care. Close it down. What you're left with is the command window. So the command window is basically a calculator. CLC clears the window, and with it I can do things like say, what is 2 plus 3? Answer is 5. I can do more complicated things. 2 plus 3 times 5 plus 6 divided by 7 plus 8 gives an answer. It's a calculator. I can assign variables. I can say A equals 2, B equals 3, C is A squared plus 2 times B. C is 10. So really what you have with Matlab, it's a calculator like any other calculator, not a whole lot different. Now Matlab is case sensitive. For example, if I say A equals 7, capital A equals 6, I can say B is capital A plus little a, 13. Matlab also uses the syntax of most programming languages. What it does is I have an operation on the right-hand side of the equal sign. It does that analysis or analyzes that equation and then assigns it to B. So I can say that A is equal to B plus 7. That's valid. But I can't say A plus 7 equals B. That's an invalid syntax. Like most programming languages, I have to do all the analysis on the right side of the equals. Once the computation is done, it then assigns it to the variable on the left side. Okay. Matlab is also a matrix language. This is kind of one of the reasons that Matlab is so useful. Matrices are just darn useful. So I can say A is start of the matrix, 1, 2, 3, 4, 5. I have a row matrix. I can say B is 1, 2, 3, next row, 4, 5, 6. I now have a 2 by 3 matrix. I can say C is B transpose. So I'm going to do all sorts of matrix operations. I can add matrices. I could say, what is B? Well, the way Matlab does it, say, what is 2 times B? It multiplies each element by 2. So I can say, what is B plus B? That's 2 times B. I could multiply matrices. I can say, what is a 3 by 2 matrix, or B transpose, times B? That would be B transpose is a 3 by 2. B is a 2 by 3 matrix. A 3 by 2 times a 2 by 3 is a 3 by 3 matrix. I can do an inverse. So let's just pick a random matrix. 1, 2, 3, 4, 5, 6, 0, 9, 1. I could say AI is the inverse of A. Inverse is Matlab syntax for the inverse. A property of a matrix and its inverse, if I multiply a matrix times its inverse, I get the identity matrix. So Matlab is, one of the things about Matlab, it makes it really powerful. It handles matrices really, really well. Note, if I do something like A squared, that's A times A. If I want to take each element of A and square it, that is the dot notation. This says element by element squaring. Take each element, 1 squared, 2 squared, 3 squared. That's different. If you ever want to do an element by element operation, that uses the dot notation. So there's dot times, dot slash, dot power. And for example, dot power. This is matrix A. To say, what is A dot hat 2? A squared, that's 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared. And that's element by element squaring, which is different than matrix square. A squared is A times A. In Matlab is a programming language. I have for loops, while loops, if statements, if else statements, if else statements. We'll be using those quite a bit. For loop, this is slightly different than Python. In Matlab, when I say I equals 1 to 4, I go all the way through 4 and then quit. In Python, if you're familiar with that language, I quit when I'm equal to 4. So slightly different than Python. Otherwise, if you've used Python, Matlab is almost identical. Not exactly, but almost identical to Python. For each of these loops, I need an end statement. And one of the knocks against Matlab is the end for loop is spelled the same as an end for a while loop. Same for an if statement. It just uses end. Indentation is decorative in Matlab, but it does help understand the code. When you type in a loop, if I indent it, it makes it easier to see where does the loop end visually. Otherwise, the indentation is decorative, unlike Python, where indentation is important. So that's the Matlab command window. It's just a calculator. There's also a Matlab script. If I go over to Matlab and I do File, New, Script, or Control-N, what a script does is this can have different commands. Like this. When I run the script, that little green arrow, it's like I just typed in that code into the command window. So if I run this, I get, something like this, I get the answer 5. What scripts are nice for is if I ever want to build up a program, I can sit there and write the script and modify it, trying to get it to work. So for example, for voltage division, if I have R1 is 1,000 ohms, R2 is 2,000 ohms, R3, the voltage then, let's do voltage division, is R1 divided by R1 plus R2 times V. And say I have 5 volts. Now when I run this, let's bring this over, make it smaller, so you can see what's going on. When I run the script, it'll run through it. What the semicolon means at the end is after the operation, don't display the results. So if I want to see what voltage is, I can say what is capital B, run it, it says the voltage is 1.66. Where scripts are nice is suppose instead R1 was 1200 ohms. Now find the voltage. Now it's 1.867 at 1400 ohms. It's 2.05. So that's kind of where scripts are nice. They let you build up a program and it's easy to modify it once you've written it. In these lectures, I'll be using Matlab scripts. That makes it easier to see what's happening in the lecture, and you don't have to sit there and watch me type in the code line by line. Another powerful function in Matlab are functions. Now what a function is a subroutine. So if I go into Matlab and I say, what is ND6 5, hope it does it. If I want to create my own function, I can do that as follows. What I do is I go under File, New, Function. You don't have to do it that way, but this kind of gives you the format of a function. I have to have the keyword function that tells Matlab that this is a subroutine. I'm going to return some variable. Here's the name of the subroutine. Like when I have the subroutine roll dice. Currently that subroutine doesn't exist, but I can create it. I'm going to roll n 6-sided dice. A percent is a comment statement. It's kind of nice, but it lets people know what's going on. I can then fill it in. Let's do D6 is let's do it this way. I'm going to go into the script window first, if I can find it. I lost my script window. Let's try this. I'm going to call this roll dice. That'll be my function. And I'm going to be building it up. When I run this, this generates a random number. That's the Matlab command for random number. Let's generate n random numbers. So create a 1x3 matrix of random numbers. I've got 3 random numbers. You can notice I can sit there and check my code as I run it. Let's generate random numbers between 1 and 6. Let's round up. That's the ceiling function. Generate 6 random numbers, round up. I now have 3 6-sided dice. Now let's take the sum of those. Once I'm convinced that I'm rolling 3 6-sided dice, take the sum. There's my answer. Now, I could just change n all the time or create a function that does that. What the first line does is this is a subroutine. It's got to match the name of the file. Matlab complains otherwise. Also case sensitive, so it's capital roll, capital dice. I'm going to return y past n. Once I know n, I calculate what y is. Don't display the results. And at that point, I'm done. So if I save that, and I try to run it, I get an error message. You cannot run subroutines, but you can call them. From the main routine, I can say, let's roll dice. And roll 3 6-sided dice. I just got 8. What I'm doing on the keyboard, I'm hitting the arrow up command. Arrow up command brings up the old commands. Arrow down, previous commands. So let's keep on rolling dice. There's 3 6-sided dice. What that does is I can say, what's the sum of 7 6-sided dice? What's the sum of 23 6-sided dice? I now have a function where I can roll that many dice. That's what functions do. Functions are really powerful. This is one of the reasons Matlab has become the industrial standard in engineering. Each company can write their own functions that are specific to their product. And part of the way that company A builds a better product than company B is over the years, they've written their own Matlab functions that lets them design things better than their competitors. So those Matlab functions are company proprietary and kind of locks the companies into Matlab. But that's kind of what Matlab does. You get to build on previous designs, build on previous functions, and keep on coming up with more and more complicated designs. Now, this class we deal with random processes, so random numbers are kind of important. We have looked at some of these already. If I just take the function rand, what rand does is generates a random number between 0 and 1. If I do rand of 1, 4, that generates a 1 by 4 matrix of random numbers. That's RAND. There's also RANDN. That generates a normally distributed random variable. That's your bell-shaped curve, going from minus infinity to plus infinity. Later on, if we want a normal distribution, we'll be using RANDN. For now, we just use rand. Numbers between 0 and 1. If I want a number between 0 and 6, just multiply by 6. If I want to roll a 6-sided die, I round up. Ceiling is round up. So this will be 4 6-sided dice. And every time I roll it, I get a number between 1 and 6. Suppose I want to do 12-sided dice. Here would be 5 12-sided dice. Some useful Matlab commands. There's thousands of commands. This is incomplete. You've got addition, subtraction, multiplication, division, raised to a power, round up, round down, round to the nearest integer, modulus, so like 123 mod 10 is 3, transpose, inverse, sum, maximum, minimum, pause. This is inputting an array. So like if I say, let's go to the command window, x is the numbers 1 through 5. That generates the numbers 1 through 5. It's just a convenient way of doing that. Don't have to type in all the numbers by hand. I could also say, let's go 1 to 5 in steps of 0.5. That goes 1, 1.5, 2, 2.5, 3. That's input a sequence. When I want to do something like plot x versus y, this is a nice way to input the numbers x. Go from 0 to 10, steps of 0.01. If you want to know how many elements are in a matrix, that's length or size. Rand is a random number, RANDN, a normally distributed random number, mean, standard deviation, variance, display, tick and talk. And there's thousands of other commands. You'll kind of get the idea as we go along. And if you ever want to use some sample code, that's what this is on Bison Academy. This is code that we use in the lectures, just save you some time typing. So anyway, that's some background on Matlab. Let's get back to the topic of this lecture, Monte Carlo experiments. Now, a Monte Carlo experiment is named after the Monte Carlo casino in Monaco. It's one way to determine probabilities. The idea is if I want to know the probability of an event, write a Matlab program to play that game one time. Once I can play the game one time, repeat, like 1,000,000 times, and then count. How many times does the event happen in 1,000,000 rolls? With that, the probability of the event then is roughly the number of successes divided by the number of rolls. So to give an idea how to do that, the Monte Carlo is actually really powerful. If I can play a game one time, I can figure out the probabilities by just repeating 1,000,000 times. That's a for loop in Matlab. So let's start out with an example where we know what the answer is. Suppose I roll a 6-sided die, and I want to know what's the chance of rolling a 1. Well, the first step is to write a Matlab program that'll roll a die one time. So what I could do is, let's just roll a single die. So this is a single die, single 6-sided die. And when I run it, there's my die roll. It's different each time I roll it. Let's see, did I roll a 1? So let's call that a variable like d6. Here what I did is I'm going to roll a 6-sided die and then check. If the d6 is equal to 1, I'll increase the variable wins by 1. And for this to work, I have to first define initialize wins to 0. What display does that says display this matrix. So when I run it, I rolled a 3 and I did not win. I rolled a 6 and it wasn't a 1. 3, 6, 3, 4. Notice I'm getting a second answer right here. This is what the semicolon does. A semicolon says do the operation but don't display the result. Take out the semicolon, it does display it. That's nice for debugging. So keep on going, and let's see if I ever roll a 1. There it is. I rolled a 1 and got a win. That's play the game one time. Once that works, let's play the game 1,000,000 times. And indentation is not necessary. It's decorative in Matlab. But I'm just going to indent it to make the code easier to follow. So I'm going to start at 0 wins, roll the dice 1,000,000 times. That's the for loop. Each time I roll a 6-sided die, check to see if it's a 1, and then print out the results. Now what I should get is 1/6 of the time I'll roll a 1. If I try it, I got a 1 166,000 times. This one right here is the last time I rolled the dice. That was d6, which doesn't really tell me much. So there's the number of wins. And it should be 166,666.666. This is a random event, so I'm not going to get exactly the correct answer every time. There is information there. When we get to a t-test, I can take these results and narrow down what the odds of are getting a 1. But currently it looks like right around 16.6%-ish, somewhere around there. That's Monte Carlo. Another command that's kind of fun, not really necessary, but kind of fun. If I type in tick and talk, this will display the execution time. This took 0.03 seconds to roll the dice 1,000,000 times. That's kind of where Matlab is nice. I can do an experiment 1,000,000 times, and it doesn't take a whole lot of execution, or a lot of my personal time to do that. That took 37 milliseconds. That's Monte Carlo. Tells you roughly what the odds are of the event. The odds of rolling a 1 on a 6-sided die is about 16.6%. Second case. Let's do something more complicated. Suppose I have a game where A rolls a 4-sided die and a 6-sided die, takes the maximum of the two. B rolls a 6-sided die. High score wins, B wins on ties. Now if you had a choice, do you want to take the 4-sided die and 6-sided die and lose on ties, or take the single 6-sided die and win on ties. Which one's better? Now personally, I don't know. It's not really clear. This is where Monte Carlo comes in. If I can play the game one time, I can throw it in a for loop and play the game 1,000,000 times. Then if A is winning more than 50% of the time, I would bet on A. So let's do that. Let's start out with a code that'll play the game one time. So let's start out where I'm going to roll a 4-sided die. And I just paused the video, typed in the code. So here's where I start with. Play the game one time. I'm going to roll a 4-sided die, roll a 6-sided die, take the maximum of the two, that's A score. Roll a 6-sided die, that's B score. If A is greater than B, meaning B wins on ties, that was a win for A. When I'm done, display the 4-sided die, 6-sided die, A, B, and wins. I'm going to use that for debugging. So when I run this, here's the D4, D6. The larger of the two is A. B rolled a 4. I lost. So try it again. Let's keep going until A wins. So there's a win. A rolled a 1, or at the D4, D6, 1 and 5. Large of the two is a 5. B rolled a 4. 5 is more than 4. A wins. So there I played the game one time. Once I played the game one time, play it 1,000,000 times. And I'm actually going to change the code a little bit. CLC clears the display. It cleans it up a little bit. I put this in a script called case2. I'm just playing the game one time. When I play the game one time, I'm displaying everything. So there's the D4, D6, A is the maximum of the two, B, C wins. Once that works, throw in the semicolons. And I won, lost, win, lost. That's playing it one time. Once that works, let's do 1,000 times. 1E3 is Matlab for 1 times 10 to the third, uses Fortran notation. I won 460 out of 100 times. Once that works, let's try 1,000,000 times. So there I won 486,000, or 48.6% of the time. Every time I run it, it takes 0.12 seconds. I'll take this out. Oops. You can see the results after each run. It's roughly 48.5% of the time. What that's telling me, if I had even money bet, I would bet on B. B's winning about 51.5% of the time. That's where Monte Carlo is kind of useful. Here's a game. I don't really know which one to bet on. Well, if I can write a program to play the game once, then I can play the game 1,000,000 times. And if A is winning only 48% of the time in 1,000,000 rolls, probably the probability of A winning is right around 40%. Now, there is information in this variability. I can use that to calculate the actual odds, but that'll be a future lecture on t-tests. Another example of Monte Carlo. Suppose I have two teams playing a match. A has a 60% chance of winning any given game, but the match is the best out of 5 games. What's the chance that A is going to win the match? Well, we're going to actually analyze this a little bit later, but for now, I can use Matlab and a Monte Carlo. If I can play a 5-game match, then I can put that in a for loop and play 1,000,000 5-game matches. So what I do is, first, can I play a single match? So here I'm just going to deal out, let's play a single match and goes from 1 to 1. I'm going to generate 5 random numbers, a 5-game match. And this is either true or false, 1 or 0. It's true if this is less than 0.6. So if I try that, get Matlab to show up. And also let's clear. So here are the games. I played 5 games, and A1 lost, lost, 1 lost. Every time I run the code, I get a different 1-0 pattern. These are the games that A won. If I add them all up, A won 3 times. That's the sum of all the 1s, is 3. B is 5 minus A. If A won 3 games, B must have won 2. If A is bigger than B, A won. So once that works, put a semicolon around everything, or after everything, and that'll tell me the number of wins. Number of wins in 1 game. If that works, try 100 games. A won 70 games out of 100, 80, 69. If that works, let's try a million games. And million games, that took 2.98 seconds. A won 68.2% of the time. Try it again. About 3 seconds later, 68.25. So knowing nothing about statistics, I can calculate what the odds are of A winning this type of series by just using Monte Carlo. A's got about a 68.2% chance of winning in this format. What the actual odds are, we'll calculate a little bit later when we get to a binomial distribution. Slightly different version. Instead of first to win 3 games, let's change it to first to win by 3 games. So this is actually a much harder problem. If A wins, then B wins, then A wins, then B wins, I'm back where I started. So you have to keep on going until somebody is up 3 games. That's the difference between a for loop and a while loop. A for loop is I just play a fixed number of games, like a million games in a series, or a million matches, 5 games in a series. That is a for loop. A while loop is keep playing until an event happens. So when I keep playing until I'm up by 3, I would do this. I'm going to start out, A starts with 0 games, B has 0 games, and keep playing until neither team is up by 3. So the absolute value of A minus B means as long as either team is not at plus 3, keep playing. Every given game, A's got a 60% chance of winning. If A wins, A gets a point, otherwise B gets a point. Keep going until somebody is up by 3. That's a while loop. Once somebody wins, I'll check. Did A win? Because somebody's at plus 3. If A wins, A is greater than B, then A won. And just for fun, keep track of what the longest series was and finish it. So if we go into Matlab, and let's just play a single series. So this was an 11-game series, and A lost. Here's a 7-game series, A won. If I want to see what's happening, I could throw in a display right here. Display the game in the series. No, display A, B, A plus B. So this is how the series progressed. And I put it in the wrong spot. I'll put it right here. So inside that infinite series, I'm going to keep on displaying what's happening between A and B. So as I do it, the series starts out. A won the first game, A won, B won. A is up 3-1, 3-2, 3-3, 4-3, 5-3, 5-4, 5-5, 5-6, 5-7, 6-7. A's down 1, 6-8, 7-8, 7-9, 7-10, B won. Once I'm convinced the program works, I can say Okay, let's run it. That was a 29-game series, A won. 3-game series, A lost. 15-game series, A won. Okay, once I'm convinced that works, let's play it for 100 matches. And A won 80 times, and the longest series was 29 games. So he's winning 71, 81, 84, 76 out of 100. Once that works, let's play million games. In a million matches, that took 0.33 seconds to play a million matches. A won 772% of the time, or 77%. So with Monte Carlo, it looks like right around 77% of the time A wins in this format. Now to calculate those odds, we'll need to use a thing called a Markov chain. That'll be later in the semester. What's nice about Matlab, it can try different things. Like suppose A had a 67% chance of winning. Now overall 89%. Suppose instead of a best first to be up by 3, make that first to be up by 7. Longest match, 165 games, and A's got a 99.3% chance if you have to be up by 7 games. Did that. Next case. I can do Monte Carlo for probabilities. So for example, a game of Farkle is kind of one of the more fun dice games, and one of those beer and pretzel games. What you do is you roll dice, and you try to get points. Different combinations of dice are worth different numbers of points. Suppose I roll 6 dice, which is how you start the game of Farkle. I roll 6 dice, and I want to know what's the chance I'm going to get 2 triples. That'd be like 3 1s and 3 5s. Or what's the chance of getting a single triple? 3 5s and garbage. Well, we'll calculate that later, but for now with Monte Carlo, I can figure out those odds if I can play the game 1 time. If I can play it once, I can play it a million times. So to play the game 1 time, what I'll do is first roll 6 six-sided dice. Here's what I start with. I just roll 6 six-sided dice. Next, I want to find out what's the frequency of each number. So I modify that program. I'm now going to generate an empty matrix of zeros, and then count. How many 1s do I have? How many 2s? How many 3s? So when I do that, here's my die rolls. I have 0 1s, 2 2s, 2 3s, no 4s, no 5s, 2 6s. And every time I run it, it'll get easier to see. I'll clear the display. So here's my die roll. Here's the frequency. I've got no 1s, 1 2, 2 3s, 1 4, 2 5s, no 6s, and so on. Okay, once I'm convinced that works, I will sort the dice in descending order. Now Matlab actually has a really nice help. If I forget the command for sort, I can type in help sort. It's going to give me way more information than I want on how to use it. Descend is the keyword for descending order. So the highest frequency number is 2. Second highest frequency number is 2. I lost information about which one it is, but I don't really care. What I want to know is, like here's the 3 of a kind. If the first number is a 3, the second number is 3, and I've got 3 1s. If I had 3 of some other number, that'd be 2 3s. I can then check for that. Once I sort the dice in descending order, is the highest frequency a 3, and the second highest frequency is also a 3, that's 2 triples. Otherwise, if the highest frequency is a 3, and since this is an else, this one failed, so the second highest frequency is not a 3, that was 3 of a kind. Let's try that. We'll keep going until I get 3 of a kind. Oops, there was one. So here I have 3 2s, but I don't have 3 of a kind for the other one. That's the 3 of a kind. Okay, that seems to work. I can play the game once, Now let's play it 1,000,000 times. And that's what this does. I'm going to roll the dice 1,000,000 times. Try it again. Roll the dice 1,000,000 times. And check. Did I have 2 threes? Did I have a single, triple? Let it go. It runs. 2.4 seconds later, I had 627, 2 triples, 31,000, single triple. So it's roughly the odds, 627 out of 1,000,000 for getting 2 triples, roughly 31,000 times out of 1,000,000 for 1 triple. And it's not exact. Again, every time I run this, I get a different answer. But it's pretty close. What those odds are, we'll calculate again later. So let's prop the power of Monte Carlo. If I can play a game 1 time, I can play it 1,000,000 times and get the odds, approximately. Final example would be poker. Let's play a game of poker and find out what are the odds of getting a full house. What are the odds of getting 3 of a kind? Well, to do that, I first have to shuffle a deck. That's what this code does. I'm going to generate 52 random numbers, then sort them. Now, rather than just returning the single variable, let's return 2. What the 2 variables do is the first one, B, is the sorted data, smallest to largest. I don't care. The second one is the order. The 45th number was the smallest one. The 51st number was the second smallest. 19th one was the third one. This right there is my shuffle deck. Those are the numbers 1 to 52 in random order. Okay, now that I can shuffle a deck, let's have the numbers go from 0 to 51. My hand are just the first 5 cards of the deck. Matlab is semi-friendly. If a typo there, it says on line 4, I got a mistake. I want a minus sign. So anyway, there's my hand. Card number 12, 47, 19, 35, 50. Now to figure out what those cards are, if I assume the cards go ace through king of clubs, ace through king of diamonds, and so on, the value is the hand mod 13 plus 1. So mod 13 goes 0 to 12, plus 1 goes 1 to 13, ace through king. The suit is first 13 cards are clubs, next 13 are diamonds, next 13 are hearts and spades. So suit goes 0 to 3, plus 1 makes it 1 to 4. So if I did that, oops. So here's my hand, card number 25, 49, 50, 46, and 3. That corresponds to the 13th card. That's the king of diamonds, the jack of spades, queen of spades, 8 of spades, 4 of clubs. That's my poker hand. Okay, now that I can deal out a poker hand, I can check for different card types. So that's dealing out a hand. To check out the types, what I'm going to do is, same as we did with the dice, I'm going to count how many aces, 2s, 3s, 4s, 5s, sort in descending order, and then calculate the frequency. So here when I run this, the highest frequency is I've got a pair. I've got 2 7s. Run it again, I've got a pair, high card, nothing matches up, pair, high card. Eventually I get something bigger than a pair. I missed it. If you want to check your code, what you could do is cheat a little bit. If that's the value, does that read as a full house? 3 of a kind and 2 of a kind, it does. So that checks my code. Looks like the code is correct. Okay, once that works, I could then check for a full house. If the highest frequency is a 3 and next highest frequency is a 2, I've got a full house. Otherwise, if n of 1 is 3, I know n of 2 isn't 3 because the first condition had to fail to get here. That'll check for a full house and 3 of a kind. I've got to initialize those variables at the beginning. And when I run this, I can see. So this is, I didn't get a 3 of a kind or 2 of a kind, or full house or 3 of a kind. Keep going, there was a 3 of a kind. That's for single hand. Once that works, throw in a for loop and roll or deal out 1,000,000 or 100,000 hands. Should be 1,000,000 hands, but I'm going to speed it up, 100,000. I run it 100,000 times, that took 3 seconds. I got 136 full houses, 2,124 3 of a kinds. And every time I run it, I get a different answer. It's random. But that's roughly the probability of a full house, roughly the probability of 3 of a kind. So with that, if I roll it 1,000,000 times, I got 1,422 full houses, telling me that the probability of a full house is about 0.1422%. 3 of a kind, I got 20,000 3 of a kinds, meaning it's about 2.09%. Different every time I run it, it is random, but that's Monte Carlo. So that's kind of what Monte Carlo simulations are. It's actually a really powerful way of calculating probabilities. And it really uses the definition of probability. The probability of an event is defined as the frequency that event occurs as the number of trials goes to infinity. What you do with Monte Carlo is I write a program to play a game 1 time. If I can do that, I put it in a for loop and play it 1,000,000 times, or some other large number. And every time I go through it, I just count. How many times did the event happen? And then the probability is roughly the number of times the event happened divided by the number of trials. That's Monte Carlo. And with that, that's lecture number 2 for ECE 341 Random Processes, Monte Carlo.